Thank you very much. And now for something completely different, which concerns fixational eye movements. I want to make you aware of your fixational eye movements because everyone is doing it all the time. So you should actually know about that. What they are is simply very small scale, unconsciously performed eye motion. They comprise microsaccades, something up to 2 degrees. And just to give you a reference, what a degree is, if you stretch out your arm, is essentially 1 degree is your thumbnail. So in principle, you should be aware of those eye movements, but your brain is just very good in making you having a continuous experience of your surrounding. And then there's something ocular drift, which is more like a diffusive kind of movement. That's not my terminology, it's coming from psychology. So the drift in that case is actually more like a diffusion kind of thing. And our question here is, like simply put, what is their purpose? And in a broader sense, are they optimized? And if they optimize, what are they actually optimized for? So what are they good for is in principle the question. And so one thing, one ingredient that comes into play, and I kindly asked you to play this video. Let's see if that works. So if you could focus on that axe for a second. At some point, you might have the experience that there is, in fact, a green dot going around when there is actually no green dot anywhere on this slide. So what you witness here is a form of adaptation. Your receptors are very good in bridging large difference in brightness, but that comes at a cost, because if you stare too long at a bright light, your receptor just turns blind. And if you don't see anything, like if you see a neutral background, then you see actually an after image, which is the color antagonist. And the color antagonist of this pink dot is just a green thing. So what that means is, if you're very good at fixating, you're actually not seeing any of the purple dots at some point anymore, because they just fade from constant stimulation. Your receptors get used to it. And what you see is just a simple green dot going around. And that is why we need some degree of movement, because otherwise the entire reality would fade. And there are actually there are certain species that experience that on a daily basis. For instance, frogs don't have those eye movements. They are very good at catching things that move very quickly, but they don't see anything of their surrounding, essentially. So we have this receptor response function, and it integrates to 0, which encodes this adaptation. So now how do we build a model in order to improve our understanding of fixational eye movements? So we take a continuous planar receptor array, which is very hard to print. So we just already project a stimulus over there. So the stimulus may be subject to optical blur because you just have a lot of gooey stuff in your eye. Then it's the connection to the visual cortex is all neurons, and they are quite noisy. So that is the stochastic component in there. And then after all, we have eye motion, and the eye motion translates into motion of the stimulus on top of your retina. So those are the ingredients. And just to give you a little reminder, what that is actually modeling is the cones in the fovea, which is your center of best vision. There are only cones there. So we like to just make this an optimization problem. How should you move in order to optimize the information that you can gather from looking at your surrounding? And I don't go into detail here, just the type of questions we can ask. For instance, if we simply want to detect a faint stimulus, how does our ability of doing so relate to the specific trajectory that our eyes take? And we work together with a group of experimental psychology who can measure. And then another question concerns localization and discrimination of different types of stimuli. And I'll tell you anything about that on my page. So thank you very much.